If you drive through any new housing development built in the last 10 years, count the rooftops. You will see ridge vents, bathroom exhaust caps, maybe a solar panel or two, but you will almost never see one of these. A spinning metal turbine sitting right on top of the roof, pulling hot air out of the attic using nothing but wind. No wires, no electricity, no motor. These things were everywhere. On warehouses, on farmhouses, on suburban homes across the United States and Australia. A single 12-inch unit moves between 250 and 350 cubic feet of air per minute in just 5 miles per hour of wind. Studies showed they could drop peak attic temperatures by as much as 37 degrees Fahrenheit and cut cooling bills by nearly 15%. And yet, they quietly vanished. By the end of this video, you'll know exactly why this happened, whether the reasons were actually valid, and how to decide if bringing one back makes sense for your own home. The idea of cooling a building without burning fuel is not new. It is ancient. Persian wind catchers, called badgirs, were designed to funnel desert breezes down into the lower levels of buildings, keeping interiors cool in extreme heat without any mechanical help at all. Buddhist monks during the Tang dynasty built ventilation ducts directly into cave complexes. Medieval European architects treated the way a building moved air as seriously as its structural integrity. Thick stone walls, narrow windows, strategic openings. The Romans used aqueducts and heavy thermal mass to regulate indoor temperatures across entire cities. For thousands of years, humans figured out how to stay cool using physics and geometry. And it worked. Then the world changed fast. The Industrial Revolution created an urgent problem underground. Deep mines needed airflow to keep workers alive. Fire-driven ventilation shafts, manually powered wooden fans, and eventually steam-driven systems emerged to push and pull air through tunnels. The British Houses of Parliament installed a blowing wheel in the 18th century. Engineers like David Boswell Reed designed forced air systems for hospitals and military barracks where airborne disease made ventilation a matter of life and death. All of these solutions required fuel, constant maintenance, and infrastructure. They worked, but they were expensive to run. The real breakthrough came in 1910 when an engineer named Samuel Ewart patented a spinning cowl designed to sit on top of a roof and pull air out of the space below it using nothing but wind. No fuel, no electricity, no human input of any kind. It was the convergence of 3 physical principles working together, and the science behind it is genuinely elegant. The first principle is Bernoulli's principle. When wind hits the curved vanes of the turbine head, air speeds up as it flows around them. Faster moving air creates lower pressure. That low pressure zone forms inside the turbine housing, and it generates a suction effect that actively pulls warm air upward from the attic and pushes it outside. This is not a passive vent, sitting there waiting for air to drift through. The turbine grabs the air and drags it out. The faster the wind blows, the harder the turbine works. The second principle is the stack effect. Warm air is less dense than cool air, so it naturally rises. In a building with soffit vents at the eaves and a turbine at the ridge, warm attic air pushes upward through the turbine even when the wind has completely died down and the vanes are not spinning at all. This is something most people never realize. The turbine still functions in dead calm conditions because the physics of rising heat keeps working regardless of wind. The third principle is the Venturi Effect. As air squeezes through the narrow gaps between the spinning vanes, its speed increases further. That increased speed drops the pressure inside the turbine housing even more, accelerating the exhaust cycle. All 3 effects work together and amplify each other. The result is continuous negative pressure at the highest point of the building, pulling hot, humid, stale air out and drawing cooler replacement air in through the soffits below. Zero electricity. The only moving part is the spinning head itself. Now here's where the data gets interesting. A study by the Air Infiltration and Ventilation Center found that installing a turbine ventilator increased attic ventilation rates by an average of 15% over a full year. When wind hit the unit from its optimal direction, the improvement jumped to as much as 50%. Separate data from the San Diego area showed that a properly installed turbine system reduced peak attic temperatures by up to 37 degrees Fahrenheit. That translated to an average energy bill reduction of 14.6%. A 14-inch unit pushes between 350 and 500 cubic feet of air per minute. And because the device consumes zero electricity, every dollar saved on cooling is pure gain. To understand why this matters so much, you need to understand what happens inside a typical American attic during summer. Solar radiation hits the roof surface and turns the attic into a heat trap where temperatures can climb past 150 degrees Fahrenheit. That heat radiates downward through the ceiling into the living space below, forcing the air conditioning system to run longer and consume more electricity just to hold the thermostat steady. According to the U.S. Department of Energy, every single degree of attic temperature increase can raise cooling load by up to 4%. In many homes, the ductwork carrying cooled air runs directly through that superheated attic space. The air literally warms back up before it reaches the rooms it was supposed to cool. Residential air conditioning alone accounted for over 6% of total U.S. electricity consumption in 2020, according to the U.S. Energy Information Administration. The turbine ventilator breaks this cycle entirely, and it does it for free. So if the technology works this well, why did it disappear? The first reason is mechanical failure. The spinning head is the defining feature of the turbine, but it is also the weakest point. Over time, ball bearings degrade from moisture, dust, and poor lubrication. When they wear down, they produce a squeaking or grinding noise that transmits through the roof structure and into the living space below. Cheaply manufactured units are especially prone to this. Over the decades, that noise gave the turbine a reputation as unreliable hardware. But the reputation was earned by low-quality manufacturing, not by the technology itself. A well-built turbine with sealed bearings can run quietly for years. The second reason is a subtle engineering problem called short-circuiting. When a turbine ventilator and a ridge vent are installed on the same roof above a common attic space, the turbine pulls air more aggressively than the ridge vent. This pressure difference can cause the ridge vent to reverse its function and start drawing outside air inward, bringing rain and snow with it instead of exhausting warm air. For this reason, roofing professionals recommend choosing one exhaust system and committing to it. And because ridge vents are simpler to install and invisible from the street, the turbine is almost always the one that gets dropped. The third reason is pure aesthetics and neighborhood politics. Turbine ventilators are highly visible from the street. In the American housing market, curb appeal drives property value. Ridge vents are shingle-over designs that are nearly invisible from ground level. Homeowners associations across the country have restricted or outright banned turbine ventilators because they disrupt the clean, uniform roof lines of modern suburban developments. Even in Florida, where state law protects energy-saving devices, many homeowners associations have worked around the law by requiring turbines to be placed only on the rear slope of the roof. That rear slope may not face the prevailing wind direction, which can reduce the turbine's effectiveness entirely. The fourth reason is regulatory pressure. As American homes have become tighter and more energy efficient, building codes like the International Energy Conservation Code and California's Title 24 have begun requiring mechanical ventilation systems that guarantee precise, measurable air exchange rates. A passive turbine's performance depends on wind speed and temperature, variables that no one controls. It falls into a regulatory gray area that code officials find difficult to certify. The turbine was not squeezed out because it stopped working. It was squeezed out because it became inconvenient for the systems that replaced it. Here is what almost no one tells you. The common belief is that ridge vents are always better, and for most new construction, that is probably true. A full-length ridge vent running the span of a standard roof provides over 900 square inches of net-free ventilation area. That is roughly double what 3 14-inch turbines would deliver, with no moving parts, no bearings, no noise, and no HOA complaints. But that comparison only holds in low-wind regions where the turbine's active suction advantage does not come into play. In hot, windy climates along the Gulf Coast, the American Southwest, and the Sun Belt, the turbine's ability to actively pull air at high volume gives it a performance edge that a static ridge vent simply cannot match. Let me give you the specific numbers on cost. A single 12-inch turbine ventilator costs between $20 and $100 for materials. Professional installation adds between $100 and $300 per unit, depending on roof pitch and complexity. For a standard 1,500 square foot attic, 2 units is generally sufficient. In a southern climate with consistent wind, energy savings can pay for the full installation within 3 to 5 years. There is also a benefit that rarely gets discussed. Proper attic ventilation prevents shingles from overheating, which extends the lifespan of the roof itself. That is an additional financial return that most homeowners never factor in. But honesty matters here, and the turbine is not the right tool for every building. In cold climates during winter, internal moisture can freeze the vanes solid, shutting the system down at exactly the wrong time. In an airtight, high-performance home where mechanical ventilation is already managing air exchange, adding a passive exhaust point can disrupt the pressure balance the entire system was engineered to maintain. If you live in a climate where heating costs outweigh cooling costs, or if your home was built to modern energy efficiency standards with a tight building envelope, a turbine ventilator may create more problems than it solves. The real story here is not that the turbine ventilator failed. The technology still works exactly the way Samuel Ewart designed it to work over a century ago. The real story is that a combination of cheap manufacturing, regulatory indifference, aesthetic pressure from homeowners associations, and the rise of modern air conditioning pushed it to the margins. According to the U.S. Green Building Council, there are now more than 100,000 LEED-certified projects worldwide as of 2022. And many of those projects are beginning to re-examine passive ventilation strategies as energy costs climb and climate pressures mount. Cities like Barcelona have implemented cooling infrastructure initiatives specifically designed to increase natural airflow and reduce reliance on mechanical systems. Smart building technology now allows monitoring and optimization of passive ventilation in ways that were impossible even a decade ago. For most homeowners building new or re-roofing in moderate climates, a ridge vent is probably the more practical choice. It is simpler, invisible, and maintenance-free. But in the right climate, on the right roof, with quality sealed bearings and correct sizing, the turbine ventilator is still one of the most effective and completely free cooling solutions ever engineered. A device that costs less than $100, runs on wind, consumes zero electricity, and can cut your cooling bill by nearly 15%. It did not disappear because it stopped working. It disappeared because we stopped paying attention.